nanohub.org.
Online simulation and more for nanotechnology.
Welcome to week 1 of Fundamentals of Nanoelectronics, this basic concepts course. And as you know, the week 1, it's titled The New Ohm's Law. And what I really want to convey to you in this week is a new way of looking at current flow, a new way that has actually developed over the last 20-25 years in the field of nanoelectronics. And it gives you a whole different perspective from the way you may have learned in freshman physics. And Ohm's law is kind of representative of what you normally learn in freshman physics. And I'll remind you, in case you don't remember what it is, I'll remind you what we're talking about. Now, before I get started, let me just clarify one thing about length scales. And that is that, as you know, this word nanoelectronics, the word nano is now kind of a household word. Everyone's heard about it. Actually, that wasn't always the case. It was like back in 2000, I think the president used it in his State of the Union address, and that's when gradually the word caught on. And now everyone kind of has heard of this word nano. And what it really stands for is the nanometer. That is, if you look at length scales, as you know, a meter, if you take 1,000th of a meter, that's what you call a millimeter. And if you go down another factor of 1,000, that's what you'd call a micrometer or a micron. And if you go down another factor of 1,000, that's when you call it a nanometer. And atomic distances, that is the distance between atoms, is typically a little less than a nanometer. That is, maybe 2/10 or 3/10 of a nanometer. So atomic distances would be somewhere down here. Okay. Now, so what's that got to do with nanoelectronics? Well, let me start by noting that in electronics, one of the most important devices is this transistor, which in its simplest form consists of a conductor that you usually call the channel through which electrons can flow between two contacts. And these contacts are usually referred to as the source and the drain. And when a voltage is applied across it, electrons from the negative terminal flow through the channel from one contact to the other, giving rise to a current in the external circuit. That's what I've called I. And V divided by I, that's what's usually called the resistance of the channel. And what a transistor is it is actually, there's a third terminal which I haven't shown here, which allows you to control that resistance. So in a transistor, you have a resistor which you can change, whose resistance you can change by several orders of magnitude by putting up voltage on it. Now, what has happened over the last 40, 50 years is this channel has people have continually reduced the size of this transistor. That the channel lengths, if you look back in, say, 1985, which would be like, say, 25 years ago, the channel length would have been, say, somewhere around here. Whereas, if you look today, the channel length would be somewhere around here. So, remember, this thing is kind of going down in factors of 1,000 from millimeter to a micrometer. So when I point here, what I mean is something on the order of 10 micrometers. Roughly. And here again, what I have roughly in mind is something on the order of, say, 0.1 micrometers. like a factor of 10. Okay? So why is it that people have been continually trying to shrink the transistor, make it smaller and smaller? Well, basically so that they can get more of them to fit on a chip in a given area. So the reason the computers of today are so much more powerful than the computers from 1985 is because today's computer, every laptop you buy, has about 1 billion transistors in it. Whereas 25 years ago, what you'd have bought would have a far fewer transistors. And you can get these numbers roughly with a simple calculation like this. So think of a chip that runs about, say, 3 centimeters. That's like an inch or so, roughly. 3 centimeters on the side. Now, if your channel length of that channel in the transistor is about 10 micrometers, then the overall transistor would take up about 10 times that much space. The reason is, of course, the transistor is not just the channel, it's got those 2 contacts also. And when you take the whole thing, that's about 10 times the channel length. So overall, a transistor then would have taken up a space of about 10 times more than this. So let's say about 0.1 millimeters. Well, so in 3 centimeters, if each one takes up 0.1 millimeters, what you can see is you might be able to fit, say, about 300 of them this way. 1/10 of a millimeter each one. If you think on 3 centimeters is like 30 millimeters, so that comes to about 300. And you could think of another 300 this way, which gives you, if you multiply it, roughly on the order of 10 to the 5th, which is roughly where things stood back in 1985. You'd have about 100,000 transistors in there. Sounds like a pretty big number, except that looking back, that looks like a very small number. Reason is that today, everything is like a factor of 100 smaller. And so, it's like you can fit in 100 times more each way. So instead of just 300, it's more like 30,000 this way. And so it's here also, it's down by a factor of, it's up by a factor of 100. What that means is that the total number you can fit into this area is like 10 to the power 4th of what it used to be. Because 100 more this way, 100 this way, overall you got 10, factor of 10 to the 4th. And that is the number I had quoted before. That's really 1 billion. And today, every laptop you buy has about 1 billion transistors in it. See? And that's what really makes it so much more powerful than what it used to be. And that's what has been always driving this industry for many years now. Now, this course, however, is really not about where this field might be going, how to make, or what the kinds of circuits this allows you to build. That's not what we are talking about. What we really want to talk about in this course is this totally different view of devices that has come about, this change in paradigm, what I've called the change in paradigm that has come about from this shrinking. And the reason is something like this. You see, if you look back to where things were in 1985, as I said, the channel length is like tens of microns. If you had looked at how electrons get from the source to the drain, as I said, in these devices, electrons have to go from one end to the other. If you look at how an electron would go through, it would be like what technically is called a random walk. That is, an electron starts out someplace, heads out in some direction, hits something, gets turned around a little, and then hits something else, turns around, hits something else, turns around, and so on. By contrast, So that's what things look like in 1985, you see. By contrast, when you look at small devices of today and even smaller devices, electrons tend to go directly from the source to the drain. I mean, the smaller you make it, the more correct, of course, this picture is. That an electron doesn't hit anything, just goes straight through. And the technical name for that is, people call that ballistic transport. It's like a bullet. Electron just goes straight through. So that's what you see today. So today's devices, when you're down here, we are talking of what's called this ballistic transport, where electrons are going through like bullets. Whereas in the past, the transport, the way electrons flow from one contact to another, tended to be what's called diffusive. That is, if you look at that picture, it's sort of like a drunken person trying to get somewhere. So it's like goes in one direction for a while, gets turned around, goes in another direction, and so on. Eventually he gets to the other end, but with a lot of detours. So that's the diffusive. That's called the diffusive transport. So this is the change in paradigm that I have referred to in this module 1.1. The title, we called it Change in Paradigm, is this idea that our entire understanding and thinking of current flow is based on this diffusive regime. Why? Because, as I said, 25 years ago, that's the only regime people knew much about. In other words, they had all the experiments that were available were all in this regime. And based on that, there was this idea that there's this general experimental observation that resistance can be written in the form of something called the resistivity, which is a property of the material of the channel, times the length of the channel divided by the width. So let me take this off. So length is the distance from source to drain, and width is this. And of course, the wider you make it, more current can flow. And when more current can flow, it means the resistance is smaller. So that's why the width appears in the denominator. And the longer you make it, the harder it is for electrons to get through. And so the length appears in the numerator. And I guess when you say Ohm's law, yes, sometimes people use it to denote the first part, namely that resistance is voltage divided by current. Now that part, though, hasn't changed, in the sense that for small voltages, current is still proportional to voltage, and that's what you'd call resistance. So when I said the new Ohm's law, what I really mean is the second part of it, this idea that resistance is proportional to the length of a channel. Because that is what you'd learn in freshman physics. That is what usually people carry in their heads. And 25 years ago, the kinds of questions people often asked that was kind of nice to talk about was, well, what would happen if I made the channel really short? Because of course in those days, the only experiments that were available were up here. Lengths were in this order of things. And people wondered, well, what would happen if you made something that was only a few atoms long? And of course, no one knew the answer, so it was kind of fun to talk about. You could go on for hours, never really quite know what it would be. And what has changed, of course, since then is that now we actually know the answers, because people are measuring all this. As I said, every laptop has 1 billion transistors which are that short. And in laboratories, of course, people can make much shorter things. In fact, people have even measured the resistance of a single hydrogen molecule these days. And what is clear now, and this is what we'll be talking about this week, is that one way to incorporate what we now know about small resistors is that instead of this L, it's like L plus something. And that, so that when L tends to 0, the resistance does not go to 0, but goes to some constant value. Because if you drop the L, there is this thing, and as we'll see, that something is the mean free path of the order, of the mean free path. What's a mean free path? Well, that's this, you see, I was drawing how an electron goes through a long device in a random walk. So a mean free path is roughly the distance it travels before it gets turned around. And you might say, well, that doesn't make sense. We were just talking about how to correct this resistance for something that's really small, where an electron goes straight through. In that case, there is no mean free path, really. And the point, as we'll see when we discuss this further, is that when you get to a short device, this doesn't mean much by itself, the resistivity. And this by itself doesn't mean much, the mean free path, because after all, electrons are going straight through. But the product means something. And that's the constant that denotes the resistance of something really short. But I'm kind of getting ahead of myself here. Hopefully all of this would be clearer by the end of the week. That is, by the end of these 6 modules. And so that's the first module. Basically, what we'll be talking about this week then is this new Ohm's law, the old one being R equals rho L over W, and the new one being this additional term there, and what it means and where it comes from.